This playlist deals with some aspects of Eurocode 2 version 2023. Watch this channel for further selected topics. This video will deal with clause 12, detailing minimum reinforcement, brittle failure, and it's about part 2. For pure tension, formula 12.2 is given. This is new because in the version 2004 of Eurocode 2, there was for brittle failure no specific formula for pure tension. Something strange is happening in this formula because there is no scale factor. The scale factor as it is used in formula 9.3, where you have 0.5 times kh, and kh is a scale factor depending on the size of the cross section, and it's between 0.5 and 0.8. Formula 9.3 is for SLS, and it's for calculating the minimum reinforcement to avoid yielding or crack control. And formula 12.2 is in ULS, and it's for brittle failure. Now, when we can now rearrange formula 9.3 into two limits, one with kh 0.5 and one with kh 0.8. And then you will see that the minimum reinforcement must be between 0.25 this and 0.4 on the other side. Compare this now with formula 12.2, and you see immediately, because FCTF can be taken equal to FCTM, you see immediately there is something wrong here. Because 12.2 is always dominant, always. So why introducing formula 9.3 when this is always dominant? A little bit strange. We will now look at bending and axial load. This is the formula 12.1 that we've seen in the previous video, this formula. Now, remember that NED is in fact, when it is tension, it's regarded as positive, and when it is compression, it's regarded as negative. So the cracking moment of the section, calculating it in a pure elastic domain without taking into account the contribution of the reinforcement, it's BH squared over 6 times the stress, maximum stress, and the maximum stress is of course FCTM, minus the actual load divided by the cross section. MR min, the resisting bending moment in the presence of NED, is in fact a function of the reinforcement, tension reinforcement, W1, the most tension reinforcement, and W2, the least tension reinforcement. So there are now, when you want to solve this inequality, 12.1, then you will see that there are many possible combinations of tension and compression reinforcement, or most tense and least tense reinforcement. There are a lot of combination ASW1 and ASW2 to cover the NED min and M crack. So now you cannot put this in one formula, one closed formula. It's getting a little bit difficult or lengthy in time to solve this problem. So now we have to make some assumptions because we have one parameter too much. The procedure is that you first determine NED min, then you calculate the cracking bending moment, but you use already some assumptions. You say it's pure elastic, and you assume that there is no contribution from the reinforcement, otherwise it's getting very difficult. So this is pure elastic calculation. Then you estimate the you estimate the required reinforcement, and you make the assumption that it is symmetrically reinforced. So compression and tension reinforcement is the same. So it's symmetrically reinforced. That's again an assumption. And then you estimate ASY, I call it ASE, and that's your first guess. E is 1, that's your first guess. Then you calculate with this value the interaction diagram with ASI. You check in that interaction diagram the combination NED and M crack of M critical. And then you change ASI until this value is minimum, and then you call it AS minimum. So this is a very lengthy procedure and absolutely not very practical. We will now just have some words about NED min. How can we calculate, or how can we determine this value? Let's suppose that we are in compression. That's the first case. Then we know NED min is negative, and NED min must be larger than minus 0.5 ACFCD. So this is sometimes a little bit confusing. So that's why I prefer to use that the absolute value of NED min must be smaller than 0.5 ACFCD. But anyway, this is the correct formulation. Now, why is there a limit in the compression force? Well, this is because at high levels of compression, the required minimum reinforcement increases to unacceptable levels. So, which is logic because you have to reinforce for the cracking bending moment. The higher the compression, the higher the cracking bending moment. So that's why there is a limit on the compression force that you are allowed to take into account. We will demonstrate this when, for instance, NED mean is a compression force. The normal force acts positive on the required minimum reinforcement, okay, because then it will be less. An interaction diagram with changing normal forces from 0 to 0.5 AC FCD shows that the reinforcement needed at NED min equal to 0 covers all other load combinations. It means that the bending, cracking bending moment equals this formula with NED ranging equal to alpha AC FCD and alpha going from 0 to 0.5. Now we will demonstrate that into an interaction diagram, and we assume symmetrical reinforcement. Then you will see on this interaction diagram, where on the x-axis it's NRD. In this graph, it's taken positive, but it doesn't matter. It's just the graph, but it should be negative, of course. But it's shown positive on this graph. But this is a compression force, and on the y-axis, it's the resisting bending moment. And you see for a chosen value of reinforcement, you got this interaction diagram, and I've plotted all the combinations, like stated here, with alpha from 0 to 0.5, which are those green dots. And you will see normally in each green dot, I should have an interaction diagram in each dot. But I've left this out of the picture, otherwise you will not see a lot. But you see immediately that for the value where NRD is 0, and then you calculate by iteration the required reinforcement, then you will see that this interaction diagram is covering all the green dots. Secondly, when the NRD increases, you will see you will go outside this interaction diagram, and then you will end up with a huge amount of minimum reinforcement. That's why this maximum limit is it. So the reinforcement needed for the combinations with NED equals to 0 covers all other load combinations. For tension, then we know the normal force is positive. We will demonstrate the procedure that we explained in the previous slide with an example. We will take a rectangular cross section, and the cross section is 600 by 300 millimeters. The concrete cover is 40 millimeters. The concrete cover is 40 millimeters. The syrup diameter is 8. Concrete quality is C3037, and the steel quality 500 MPa. We have to make assumptions, otherwise the solutions are infinite. The assumption is that it's a symmetrically reinforcement, so bottom and top the same reinforcement, and the cracking bending moment is independent of the reinforcement. With those two assumptions, we calculate the cracking bending moment, which is now easy. It's 300 times 600 squared divided by 6. FCTM is 2.9 megapascal, and NED in our example was 250 kilonewton, and AC is 300 times 600. The units here are not mentioned, and if they are not mentioned, I always use megapascal and millimeters as basic units. And then the bending moment is 27.2 kilonewton meter. We can now see it's a part of the interaction diagram because the solution was situated in a corner, and so I had to enlarge it to make it more clear. Then now we determine AS min. We guess, or to determine AS min, we guess the reinforcement. You guess it. And by the use of an interaction diagram, we check the load NAD min M critical or M cracking. And this is an iterative process. You have to recalculate the interaction diagram for each reinforcement that you try. And now this is only the result that I'm showing. You will see that there is a minimum reinforcement of 326 square millimeters bottom and top, sorry. And this minimum reinforcement can balance the 250 kilonewton and the 27.2 bending moment, which is exactly that point. So you will see it's fairly cumbersome to calculate the minimum reinforcement for brittle failure with bending moment and a tension under bending moment and an actual force tension. Another element, when bending moment is smaller than the cracking bending moment, can happen at ULS, and the member is designed as a statically determinate without the requirements for distributed cracking. A sudden collapse after cracking, which is brittle failure, a sudden collapse after cracking may also be avoided with a minimum reinforcement designed for following resistance. So this is what will you do when the applied bending moment is smaller than the cracking bending moment? Well, then, first of all, I do not understand what it means without the requirement for distributed cracking. This is something new for me. I thought this was always the case, but apparently not. So I was wondering, when is this the case? Or when is this not the case? Anyway, so when the bending moment is smaller than the cracking bending moment, then you can calculate the needed reinforcement for brittle failure with the formula 12.3. It means that you have to put the reinforcement in the section, in the cross section, that not fulfills the cracking bending moment, but the KDC MED bending moment. It is the actual external bending moment multiplied by coefficient KDC, which is depending on the ductility class of the steel. So it goes from 1.3 to 1.0. The most common reinforcement steel has a ductility class B. So if you don't know, you choose B. So the coefficient is 1.1. Eurocode 2 version 2004 uses the factor 1.2 independent of the ductility class. So we have, in principle, a reduction. For members with brittle failure, for members where brittle failure due to tensile stresses is excluded, such as members in compression and members with no structural function, minimum reinforcement for brittle failure, longitudinal and transversal, may be regarded. Brittle failure in transversal direction for beams means in fact the stirrups. For slabs, it's logic. It's also a longitudinal reinforcement, but in the other direction. So the last element is the minimum reinforcement for brittle failure, but for shear and torsion. And this, there you have a minimum amount of stirrups or bent up bars. And this minimum amount depends on the ductility class of the reinforcement of the stirrups and is given by this well-known formula. You will notice that this is the formula that was applicable in the version of 2004, independent of the ductility class. Now you see that for other ductility classes, you can have less minimum shear reinforcement. We will now make a comparison between the version of 2004 and the version of 2023 for a cross-section 600 by 300, a stirrup diameter of 8, concrete quality C30, and steel quality B500 or 500 megapascal. And we will do that by assuming, of course, in Eurocode 2, it's independent of ductility class, and we will make the comparison with the version of 2023 with a ductility class B, which is the most commonly used ductility class. So we will use this formula for the stirrup density. You see, we have chosen here for 2 legs. The cross section with diameter 8 is P8 squared over 4, divided by the distance between 2 stirrups and divided by the width. The stirrups are vertical, so sinus alpha is 1. And then we see that for S, the distance between the stirrups must be smaller than 380 millimeters. So you have a diameter 8, 2 legs at a distance 380 millimeter will fulfill the minimum shear force reinforcement. In the proposed code 2023, we use this formula with 0.072. We fill in all the unknowns, and we have S, which must be smaller than 425 millimeters. So you see that we need now less reinforcement, and you see now what is the difference between the two. Is between 380 and 425. Minimum reinforcement should generally be anchored and lapped according to clause 11. We will handle this clause 11 in other videos. So the minimum reinforcement, most engineers forget about that. Minimum reinforcement is also subjected to anchoring and lapping. And in this clause, it says that that it should be anchored for a design stress sigma SD equals to FYD AS min divided by AS, where AS is the actual reinforcement area provided. So when you put a little bit more, which is normally the case, minimum reinforcement, than the required minimum reinforcement, then you can have some reduction in the anchorage and lap length. Reinforcement provided only to satisfy minimum steel requirements may, at simple supports, have its anchorage length reduced, providing that it is bigger than 10 times the diameter, past the inner edge of the support. So this is clear. You should always obey those this length, this anchorage length of 10 times the diameter of the rebar used. Then let's go further on this aspect. You have two cases. Or the design tensile stress in the concrete is FYD, or the design tensile stress is smaller than FID. And then you will see that the anchorage length, LBD, is proportional to this formula. So it's proportional to two different elements. The first one gives you a reduction, or if FIK, the characteristic value of if FID is smaller than 435, then you can have a reduction factor 1 and a reduction factor 2 when you put more reinforcement than the required minimum reinforcement. So don't forget, you have two reduction factors. It is not proportional to the power 1, but to the power 1.5. In the second case, when the design tensile steel stress for your minimum reinforcement is smaller than FYD, then you use, of course, this formula. FID is then replaced by sigma SD, which is the lower value. But now, what happens if sigma SD is bigger than 435? So we have seen in clause 9.22 that you can calculate minimum reinforcement for crack control, where not crack control, but for yielding of the reinforcement, where sigma SD is taken equal to 500 megapascal, for instance, or it can also be 600 or 700, then you will see that this lap length will be increased because this factor will be dominant. So this means that the lap length for minimum reinforcement to avoid yielding, where sigma S is equal to F to the yield strength of the concrete, of the steel, of the reinforcement steel. So the lap length for minimum reinforcement to avoid yielding is much larger than the lap length for the minimum reinforcement for crack width limitation. So this is interesting to know, and that you can save some kilograms of reinforcement by using this rule.